All right, today we are diving headfirst into one of the most foundational, coolest pillars of artificial intelligence, expert systems. We're going to look at how AI first tried to bottle lightning, to capture and replicate the decision-making power of a human specialist.
So here's our game plan. First, we're going to get into the why, the whole ambition to clone an expert's brain. Then, we'll peek under the hood at the blueprint of these digital minds. After that, we'll meet some absolute legends of the AI world and uncover the secret sauce for capturing expertise. And finally, we'll deliver the verdict on their lasting legacy. Let's jump in.
Okay, first things first. Why did AI even need a specialist? Well, this entire field really grew out of a very specific and, let's face it, a very human problem.
I mean, just think about it for a second. What if you could take the world's best doctor, or chemist, or engineer, and just copy their brain? Make all that knowledge available to everyone, everywhere, at any time. That is the core idea. The problem, of course, is that human experts are an incredible, but very limited resource.
And when you really break it down, the limitations are super practical. Top-tier experts, they're expensive, and there just aren't enough of them to go around. They can't work 24/7, they get tired, and let's be real, even the absolute best of us make mistakes. So there was this huge, clear need for a way to preserve and scale that invaluable knowledge.
And this is the solution that early AI pioneers came up with, an expert system. Now, this isn't just some big database of facts. It's a program specifically designed to mimic the decision-making and problem-solving abilities of a specialist in one particular field. It was literally an attempt to digitize expertise itself. Okay, so we know why they were created. Now let's get into the how. How do they actually work? We are going under the hood to look at the blueprint of this so-called digital mind.
The best way to think about it is like you're building a brain. You don't just have one big blob of thought, right? You have different parts that are responsible for memory, for reasoning, for communication. Well, an expert system is structured in a very similar, very modular way.
At the very core, the heart of the whole thing, you have the knowledge base. This isn't just raw data. This is the expert's wisdom, distilled into facts, and this is the key part, rules. It's basically a digital library that holds everything the expert knows about their specific domain.
And this is a perfect, super simple example of how that knowledge is structured. The whole system runs on these logical if-then statements, which are often called production rules. So here, the rule connects symptoms to a diagnosis, pretty much exactly how a doctor thinks. A real knowledge base would be packed with hundreds, maybe even thousands of rules just like this.
Now, if the knowledge base is the library full of books, the inference engine is the smart librarian who actually reads the books and makes all the connections. It's the active, thinking part of the system. It takes the facts of a new problem, like a patient's symptoms, and it just systematically applies the rules from the knowledge base to figure out what's going on.
And then to make the whole thing work, you've got a few other key parts. The working memory is kind of like a temporary notepad, just for keeping track of the current problem. The user interface is, well, how we talk to it. And the explanation facility, and this is incredibly important, is what allows the system to justify its answers, just like a human expert would.
Okay, so we've got the theory, we've got the architecture. Now let's see how all these pieces came together in some of the most famous and influential expert systems ever created. It is time to meet the pioneers.
We're going to zero in on two absolute legends, MYCIN and DENDRAL. Now, they operated in completely different fields, medicine versus chemistry, and they even used different ways of thinking. MYCIN used something called backward chaining, which means it started with a possible diagnosis and then worked backward to see if the evidence fit. DENDRAL, on the other hand, used generate and test. It created all possible answers first and then checked them. As you'll see, MYCIN was famous for being able to explain itself, while DENDRAL has the huge honor of being the very first of its kind.
So let's open the case file on MYCIN. Developed back in the 1970s, its job was to diagnose bacterial blood infections and recommend the right antibiotics. Its knowledge base had something like 600 rules, all gathered from top doctors. But its real superpower was that explanation facility. A doctor could literally type in, "Why did you ask me that question?" or "How did you reach that diagnosis?" and MYCIN would show its work, step by step. That kind of transparency was absolutely revolutionary for building trust.
And then there's DENDRAL, basically the grandfather of them all. From way back in the 1960s, it tackled this hugely complex problem in chemistry. Its method was a perfect example of generate and test. It would systematically generate every single possible chemical structure that could fit the data, and then use its knowledge base of chemical rules to test and eliminate the wrong ones, until only the most probable one was left. DENDRAL was the system that proved this whole crazy idea could actually work in the real world.
Okay, so these systems are clearly powerful. But that brings up a really critical question. How do you get all of that incredible, nuanced human knowledge out of an expert's head and into a machine in the first place? This right here is the secret sauce.
The official term for this is expertise transfer. You can think of it as the bridge between the complex, often intuitive knowledge in a human mind and the structured, logical format that a computer needs to understand. And honestly, this is often the hardest and most time-consuming part of building an expert system.
And it's not a one-shot deal. It happens in a cycle. First, a specialist called a knowledge engineer has to acquire the knowledge, usually through intense interviews and just watching the expert work. Then, they have to represent that knowledge as those if-then rules we talked about. Finally, and this is so important, they validate the system by throwing real-world test cases at it to see if it performs as well as the actual human expert.
All right, time for a truly expert-level concept, meta-knowledge. This is what separates a novice from a true master. It's not just about knowing the rules of the game, it's knowing how and when to use those rules. You can think of it as the system's strategic layer. It's knowledge about its own knowledge.
So here's the crucial difference. Standard knowledge tells the system what to do. Like, if you see a fever, then you should suspect an infection. But meta-knowledge provides the strategy, the rules about the rules. It might be something like, always check for the most life-threatening conditions first, or if two rules are telling you different things, trust the rule that came from the more reliable source. This is what elevates the system from a simple rule follower to a much more intelligent reasoner.
Wow. Okay. We've gone from the basic idea to the blueprint, and even into the really advanced strategies for capturing knowledge. So for our final section, let's deliver the verdict. What is the actual lasting legacy of these pioneering systems? Where are they now?
The scorecard is pretty clear, really. On the plus side, they are incredibly consistent, they're always available, they're fast, and they can explain their logic, which is huge. But they have some major drawbacks. They're unbelievably narrow. A medical expert system knows absolutely nothing about chemistry. They have zero common sense. And, as we just saw, getting all that knowledge into the system in the first place is a massive bottleneck.
So while we don't really see these huge custom-built systems like MYCIN very often anymore, their legacy absolutely lives on in what we call expert system shells. Think of it like a ready-made template. The shell gives you the pre-built inference engine and user interface. All a developer has to do is plug in their specific knowledge base, the rules for their new domain. It makes the whole process so much faster and more accessible. And in a way, this kind of explicit rule-based logic was really a conceptual ancestor to many modern AI systems that still rely on structured knowledge.
And that leaves us with one final thought to chew on. Expert systems prove that a huge chunk of expert decision-making, the logical, rule-based part, can definitely be captured and automated. But they also revealed what couldn't be easily coded. Things like common sense, creativity, and that gut intuition to know when it's time to break the rules. So the question remains, what is that truly irreplaceable spark in human expertise?